Hi, everybody. So we're ready to move into Chapter 9, which is a continuation of the discussion of different ways of looking at proofs. Chapter 9 is about disproofs. In some ways, there's really nothing new to disproving something because if a theorem says such and such is true, then a disproof says such and such is not true. And so in some sense, disproof is about proving the negation of a statement, but then you still have to prove it. So we're going to look at some examples of this, but before we do that, I want to maybe give you a little bit of a history of a famous problem in mathematics that is some kind of an indication of how mathematics as a science moves forward. And this is relevant to this discussion because in between something being sort of just a speculation and then it becoming a theorem or being disproved, it passes through a stage known as a conjecture, which is a statement which you have some reason to believe is true, but you are unable to settle for sure whether it's true or false. So I'm going to tell a little story. So, as I said, you can think of the progress in mathematics as a cycle where people formulate conjectures. And remember, a conjecture is a statement which you have some reason to believe is true, but you are unable to settle whether it's true or false. It's an unknown. Its truth value is unknown. And mathematicians formulate conjectures, and then they try to settle whether they are true or false, and therefore either prove or disprove them. And you end up with a cycle where you have a conjecture, and maybe you get a proof of it, and it becomes a theorem. And then that theorem suggests new ideas, which leads back to a conjecture. Or you have a conjecture which turns out to be false, and it gets disproved. And that leads to exploration, try to fix what went wrong, what caused the conjecture, what about the conjecture made it be false. And then you reformulate the conjecture, and it goes back to being a conjecture. And I think I've mentioned a few of these big conjectures out there. Many people have heard of the Goldbach conjecture, which says that every even number is a sum of two primes. So this is not proved, but that doesn't mean there hasn't been a tremendous amount of progress on it. And the kind of progress is that people have shown, for example, that every even number is a sum of two numbers, one of which is prime and one of which has only two prime divisors, at most two prime divisors. And that's not quite the full force of Goldbach's conjecture, but it's in the right direction. And there's a lot of reason to believe that this is probably true. Another elementary number theory conjecture is the twin prime conjecture, which says that so a twin prime is an example. So 3 and 5 are twin primes. 11 and 13 are twins. So they're primes separated by 2. So a twin prime is a pair of primes that are 2 apart. And the conjecture says there are infinitely many, and it's not known. Are there infinitely many such pairs? But there's been a lot of progress on this. For example, it's known that the gap between successive primes can be very small, and you still have infinitely many. And the question is, can you get that down to 2? And this is another area where there's a lot of work recently. And I've also mentioned the Millennium Problems. So the Millennium Problems, there's a link to them on the course page. These are worth $1 million each, and each of them is in a sense a conjecture. That is to say, it says, we believe the following is true, and if you can prove it or disprove it, you'll get $1 million. And also a lot of fame and fortune. So it's worth a lot more than $1 million in practice. They're also very hard. But the story I wanted to tell is about a different problem, which began life back in Greek Alexandria, back in the 3rd century, roughly speaking, with an individual known as Diophantus. And Diophantus published a book which he called Arithmetica, and Diophantus was a little bit like Euclid. He was sort of from the same culture, lived a little bit later. But whereas Euclid was interested in geometry, Diophantus was interested in number theory mainly. Of the 13 chapters in his book Arithmetica, we have 10 of them today. Amazingly, we had 6 of them up until very recently, and then 4 more chapters were found in a Persian library within the past, 25 or 30 years. So for, several thousand years, we knew about only 6 of these chapters. And the reason the Europeans knew about them is because the work had been translated into Arabic and Persian and had been studied by scholars in those cultures for many years. And then during the Renaissance, these works were translated into Latin, and Europeans became interested in them again. So there's a lot of interesting stuff in Diophantus's book Arithmetica, but the thing which is kind of I always think about is that it's in this book that there's a discussion of Pythagorean triples. So as we've seen, a Pythagorean triple is a triple of natural numbers that satisfy Pythagoras' theorem. And we always think of the 3, 4, 5 triangle because 5 squared is 3 squared plus 4 squared. This is probably the most famous example. It goes back to ancient Egypt. But Diophantus actually showed that there are infinitely many of these triples, and he gave a way to construct them. Namely, you take u and v to be natural numbers, and it's best to take them with no common factors for reasons that I'll say in a minute. But having picked u and v, you let a be u squared minus v squared, b be 2uv, and c be u squared plus v squared. So if I take u equals 3 and v equals 2, then u squared is 9 and v squared is 4. So u squared minus v squared is 5. 2 times u times v is 12. And u squared plus v squared is 13. And what Diophantus points out is that any set of numbers a, b, and c that you construct in this way form a Pythagorean triple. And in fact, here's one. So this says that 13 squared is 12 squared plus 5 squared, which it is. This is 169. This is 144 plus 25. And the reason I said you should take u and v not to have any common factors is not because it won't work. If you take u and v to have a common factor, you'll still get a Pythagorean triple. But you'll get a Pythagorean triple where the a, b, and c have a factor in common that you could have divided out, so they're not as interesting. Nevertheless, this shows that there are infinitely many Pythagorean triples. So, as I mentioned, these 6 chapters of Diophantus that were known to the at least in relatively common circulation in Arabic culture, were translated back to Latin during the 16th century as part of there was a lot of flow of material out of the Islamic conquests back into Renaissance Europe. And this book was one of them. And eventually a French lawyer in Toulouse by the name of Pierre de Fermat, who had become interested in mathematics, comes across Diophantus's book. Now, Fermat made many contributions to mathematics, but the one that he's probably most famous for starts with his reading of Diophantus's book. And having seen Diophantus's discussion of c squared equals a squared plus b squared, he made the kind of step that advances mathematics, which is that he asked a very straightforward generalization of that question. He said, what if you make the power 3? Can you find natural numbers so that c cubed equals a cubed plus b cubed? Or even maybe not just natural numbers, maybe it would help you if you allowed negative numbers. So he was prepared to allow non-zero negative numbers as well into his equation. And never mind just 3, what about higher powers? And you could think of these as Fermat triples. If you could find a, b, and c, so that c cubed equals a cubed plus b cubed, or c to the fourth equals a to the fourth plus b to the fourth, or c to the fifth equals a to the fifth plus b to the fifth. And he asked, are there any like that? And he proved that there are no solutions to this equation in natural numbers or even in integers that aren't zero for the case n equals 3 or n equals 4. And that was an impressive result. And then in the margin of his copy of Diophantus's Arithmetica, he wrote, there are no solutions in natural numbers to the equation c to the n equals a to the n plus b to the n for any n bigger than or equal to 3. I have a wonderful proof of this proposition, but the margin of this book is too small to contain it. And he never published any more work in this area. And then this note in the margin was found by Fermat's son after Fermat died. So this is an example of, Fermat asked a natural question. He knew from Diophantus a lot about this equation, so he asked about these more general ones. And then he claims, or seems to have claimed, that he has proved this very general result. But it's very unlikely that he actually did. And if he had, he probably would have written a complete proof down. So this became known as Fermat's last theorem, but it should really have been called Fermat's last conjecture. And his Fermat's last conjecture says that if a, b, and c are integers, and none of them 0, then, and n is bigger than or equal to 0, and n is bigger than or equal to 3, then c to the n is not equal to a to the n plus b to the n. So in other words, there does not exist a solution to the equation c to the n equals a to the n plus b to the n. The reason you have to put in none of them 0 is because, of course, if b were 0, you could take a equals c. So you have to rule that out. And that's a big conjecture. And for 350 years, people worked on this. And there was progress over that period. And in fact, entire branches of mathematics were invented in order to try to explain, to settle whether this theorem was true or not. I mean, it could be false. It's possible that for, n equals 7,367, there is an a, b, and c that satisfy this equation, but they would have to be enormous. So people tried all kinds of different things. And in the 19th century, a mathematician named Kummer probably made the most progress of anybody, but it was still unsolved up until the time I went to graduate school, which was in the early 1980s. Also, a lot of people claimed proofs, but they turned out to be wrong. But in the 70s and 80s, people saw a way that might be possible, a completely new way that might give them a way to prove Fermat's last theorem or Fermat's conjecture. And in 1994, using everything that had been done before, Andrew Wiles announced a proof, and then it turned out that his proof had a mistake in it. And then he was able to recruit another mathematician named Richard Taylor, and together they were able to fix the proof, and Fermat's conjecture finally became a theorem after 350 years. So during all that time, this question about whether or not there existed a solution to these equations was not known. No one knew of any solutions. I mean, that would have been one way to settle it. But a lot of computer searches were done when that became possible. Nobody found a solution, but it took really the work of hundreds and hundreds of people over 350 years to finally settle this equation, plus some really brilliant insight by Andrew Wiles. There are some good books about this if you're interested in learning more about it, and even a NOVA program that you can get a hold of if you look around on YouTube or places like that, if you're curious. So that's the story of Fermat's last theorem. And as I mentioned, there are many, many unsolved problems still out there. And people solve some of them, and that raises more questions. And mathematics continues to be a living subject.